Today, we are going to embark on a journey through space and time, from our galactic neighborhood all the way to the largest structures in our cosmos. On what we find to be the most imposing in the universe, if we set aside the universe itself, and what we call the end of immensity. But before I take you to crash into this immensity, give me a few minutes to lay the groundwork and set the scene of the uneven distribution in the form of a celestial tapestry. What form does matter take on large scales in the universe? As a starting point for this journey toward the edges of the cosmos, let's randomly choose a galaxy, ours, the Milky Way, which we see here in an artist's rendering. At the start of the last century, it was the sole known galaxy. Today, we have trouble even estimating their number. They are found everywhere, no matter which regions of the deep sky we look at. And above all, with the progress of telescopes, by probing the universe on a large scale, we realize that these galaxies, contrary to what we might have thought, are absolutely not distributed uniformly in space. Like stars, they cluster together, and 95% of them live in groups gathered by gravitational effects. Thus, the deep sky is stained with gigantic galactic gatherings, linked to each other across space by the sole force of gravity. Galaxies group together to form enormous clusters stretching across extraordinary distances. Let's begin with the groups we belong to and gradually increase their size. Our galaxy, the Milky Way, with its 100,000 light-years in diameter, belongs to what we call our local group. On the scale of the universe, this group, which takes the shape of a sphere about 10 million light-years in radius and contains around 50 other galaxies, is just next door. And as large as it is, our local group is relatively modest in size when compared to the Virgo cluster. Located 50 million light-years away, it contains 300 times more galaxies than our local group. And all of this is packed into a volume that's only slightly larger. This giant cluster is just one of many others we find around us, and which, like vast galactic clouds, share a common landscape and are grouped into an even larger structure, known as the Virgo Supercluster. And stretching over more than 110 million light-years, the Virgo Supercluster is a monster of space. And I don't use that word lightly. 7,000 times more massive and voluminous than the local group, it alone contains about 10,000 galaxies grouped into 100 different clusters. To try to give you an idea, imagine that if our local group were a scattered cloud, the Virgo Supercluster would be the entire stormy sky. Except, of course, beyond this supercluster, the web, the universe continues, and beyond that there are even more superclusters. Like the Coma Supercluster with about 36,000 galaxies, and Corona Borealis, which has 76,000, or even the Perseus and Pisces Supercluster, which form a great wall stretching nearly 300 million light-years. In short, superclusters are literally found everywhere, no matter which direction you look. The number of these superstructures is estimated to be several million in the observable universe. Given the vastness of superclusters, we once believed we had reached the limits of immensity. Because on ever larger scales, these structures seem to form long filaments together, with which we begin to see lines of higher density and areas of darkness taking shape. Voids whose boundaries, blurry and difficult to define, take the shape of a strange and gigantic cosmic web. A web woven from filaments. Galactic filaments billions of light-years long and containing hundreds of thousands of galaxies. To grasp the immensity of this web that you are flying over at an impossible speed of 20 million light-years per second, keep in mind that literally every point making up these filaments in the image corresponds to clusters of galaxies. That's the setting that stretches across the universe all the way to its edges, where our view stops at the limits of the observable universe. And from then on, a question arose. This cosmic web, whose structure is driven by gravity and the expansion of space, is it a network, a vast, coherent cosmic whole? This big question made us reconsider what we thought was the limit of immensity. As you'll see, you may find an even greater answer there. It was long believed that beyond supergalactic clusters, something halted. Not the universe itself, which of course continues beyond that, but the escalation in the size of structures, the end of a certain kind of architecture. Because at even larger scales, we begin, at least on paper, to reach the upper limit of what gravity can hold together, can bind. For a long time, people believed these superclusters, forming huge filaments, marked the limits of immensity. It seemed to us that at scales even larger than these, it was impossible to form coherent structures, to find even larger structures whose elements are bound together. They would be bound by gravity. In other words, these superclusters were considered the largest coherent structures that could be found. Beyond that, hierarchical structures disappear and everything appears uniform and unstable. The filaments making up this cosmic web were assumed to be the scale at which everything merges together, in a kind of homogeneous framework, devoid of discernible structures, where each part of the web is similar to the others. Or, at this level of detail, all regions of the universe seem to look alike. All matter appears to us as being uniformly distributed in all directions. And that's it, the end of immensity, a boundary beyond which the roughness of the universe's large structures disappears, and which appeared at observation scales of around 300 million light-years. But recent and puzzling discoveries seem to have revealed structures whose mind-boggling sizes push those limits even further, and in a sense shatter this end of immensity. At the intersections of vast filaments, galaxy walls have been found that are 200 times larger than the Virgo supercluster, and on which thousands of clusters seem to align over such vast distances. And I stretch my words when I say that they defy the size limits of structures we thought could be gravitationally coherent. The first observation of these galactic walls pushing back the end of immensity was certainly that of the Great CFA2 wall, where, over 500 million light-years in height, 200 wide and 15 thick, an unusually high number of galaxies are concentrated. And this wall, marked by the seal of excess, is now only the fourth largest known cosmic structure in the universe. Because other discoveries of this kind have followed. They are called the Sloan Great Walls, or the South Celestial Pole Wall, both of which are nearly twice as large as the CFA2 Great Wall. And they cover nearly 1/60th of the diameter of the observable universe. Each one contains hundreds of thousands of galaxies and tens of thousands of quasars spread across the cosmos over nearly 1.5 billion years. The Great Walls of Hercules and the Corona Borealis span light years. Titan was discovered during efforts to detect gamma-ray burst alignments in the deep sky. There, scattered over more than 10 billion light-years, we find nearly 4 billion galaxies, which makes it by far the largest and most massive structure known in the observable universe. The existence of these giants, nearly 10% the size of the observable universe, raises even bigger questions than the structures themselves. How can such seemingly structured gatherings exist if, as we believe, no coherent structure, more than 1 billion light-years wide at most, should not have had time to form since the birth of the universe? Indeed, as massive as they are, galaxies, like the hypothetical dark matter that quietly seems to help shape their distribution in space, are not able to influence each other over such monumental distances. Or to put it simply, the universe is too young for them to have had the time. And that is why these discoveries, by pushing the boundaries of the end of immensity to the scale of 1 billion light-years, present a challenge to our understanding of the universe. We still don't really know if, strictly speaking, these arrangements are actual structures in the astronomical sense, if their components are gravitationally bound to each other as the visible parts of a vast underlying superstructure, or if they are just groupings of smaller walls, filaments that chance has temporarily brought into alignment. But in reality, they have no common origin, nothing of a true structure. In any case, if it turns out in the future that these walls are gravitationally coherent structures whose elements have had time to influence each other over the course of their history, then that would call into question some of our ideas about the limits of cosmic size. Regardless, the search for the universe's largest structures and ultimate framework continues, because of their size, their distance from us, and their many components. It remains very difficult to determine precisely where these cosmic cathedrals begin and where they end. Especially since, at these scales, things are not always as they seem to be. Indeed, just to add a bit more difficulty to all this, at the scales of observation, clusters and superclusters alike, Phenomena such as gravitational lensing or shearing can create visual mirages in our telescopes, adding to our observations some magnificent light aberrations, as you can see here. In this cluster of galaxies, the massive foreground mass bends the light rays coming from the background galaxies. Today, we try to unravel the mysteries at the edge of the vastness. We can also use amazing simulations that incorporate our theories into their calculations, as well as the data gathered and compiled from our observations. And these simulations allow us to look into aspects of the universe that are otherwise difficult to access for now. So, using the power of digital technology is an indirect way, a shortcut to reach a clear vantage point, giving us an overview of the universe and its large structures. What's wild is that these powerful simulations can show us how matter is distributed in the universe, achieve results in the cosmic web that align with real-world observations. That is, a three-dimensional picture in which clusters of galaxies intertwine, connect, and pile up. On large scales, it takes the form of a cosmic web made of vast interconnected filaments that can even create walls, vast strokes whose brush lengths seem to be limited to billions of light years long. Infinity, real or simulated, always overwhelms me.